Intelligent Transportation Systems Podcast. Welcome back to the ITSPodcast. This is episode 36 for September 2016. This is Javier Sanchez Medina speaking from the Intelligent Transportation Systems Society. Are you there again? Well, that's great news. Thanks. How's summer unfolding? Did you get the chance of resting a little bit? Well, here's something you can add to your vacation plans. You can listen to this fantastic new issue we have put together for our selected audience. We have included a special content this time, nothing less than the Professor Philippe Crane's keynote talk at our last ITS Society's ITSC 2015 conference in Spain. Philippe Crane is chair of the IEEE Transportation Electrification Community and delivered a very interesting and provocative talk titled Leveraging High-Performance Electric Transportation for Intelligent Systems. We also have a news mini section by the assistant editor Dr. Marian Kaveshkar, who has compiled a couple of very interesting stories about Uber and Tesla's recent accident. Mehran Shirazi will be talking about supersonic passenger flights in his Transportation History mini section, and finally Haluk Eren has done a very interesting book review on the book titled Incremental Learning for Motion Prediction of Pedestrian Vehicles. And that's it. Thanks very much for listening. Let's start now. We hope you enjoy it.
This is the news mini section for September 2016 by Mariam Kaveshkar. By end of this month, Uber will allow its customers to call driverless cars by their phone. Well, almost driverless. For now, Uber's test cars travel with safety drivers as common sense and the law dictate. These professionally trained engineers sit with their fingertips on the wheel, ready to take control if the car encounters an unexpected obstacle. A co-pilot in the front passenger seat takes notes on a laptop, and everything that happens is recorded by cameras inside and outside the car, so that any glitches can be ironed out. These were the words of Rafi Krikorian, Uber's engineering director. Uber's Pittsburgh fleet consists of custom Volvo XC90 sport utility vehicles outfitted with dozens of sensors that use cameras, lasers, radar, and GPS receivers. Uber plans to partner with other automakers and recruit more engineers. Speaking about lasers, Elon Musk believes that there is no need to use LiDARs in autonomous cars. Maybe after the tragic accident of Tesla in July, he has to give it a chance. Google, unlike Tesla, takes advantage of LiDARs made by Velodyne. However, the cost issue is the main fallback of this sensor. We want the cost to be low enough to be used for all cars, said Martha Hall, Velodyne's president of business development, in a statement. The funding is the latest validation of Velodyne's LiDAR sensors, which were first used in autonomous driving experiments a decade ago. In 2007, almost all the cars that finished the DARPA Urban Challenge were equipped with Velodyne's LiDAR. The company raised $150 million in funding to develop better laser imaging technology, or LiDAR for driverless cars. Ford and China's search engine company Baidu led the funding round with $275 million investments. In short, drivers have to find an alternative job. Subscribe for more news.
Transportation in History by Mehran Shirazi, PhD candidate at Simon Fraser University, Canada. Supersonic transport. A supersonic transport, or SST, is a civilian supersonic aircraft designed to transport passengers at speeds greater than the speed of sound. To date, the only SSTs to see regular service have been Concorde and the Tuple of Tu-144. The last passenger flight for the Tu-144 was in June 1978. Concorde's last commercial flight was in 2003. Following the permanent cessation of flying by Concorde, there are no remaining SSTs in commercial service. Supersonic airliners have been the objects of numerous recent and ongoing design studies. Drawbacks and design challenges are excessive noise generation at takeoff, high development costs, expensive construction materials, great weight, and an increased cost per seat over subsonic airliners. Despite these challenges, Concorde was operated profitably in a niche market for over 27 years. Serious work on SST design started in the mid-50s, when the first generation of supersonic fighter aircraft were entering service. It was the Anglo-French development of the Concorde that set off panic in the US industry, where it was thought that Concorde would soon replace all other long-range designs. The Soviet Union set out to produce its own design, the Tu-144, which the Western press nicknamed the Concordski. The SST was seen as particularly offensive due to its sonic boom and the potential for its engine exhaust to damage the ozone layer. Nevertheless, in the mid-70s, 6 years after its first supersonic test flight, Concorde was now ready for service. The US political outcry was so high that New York banned the plane. This destroyed the aircraft's economic prospects. It had been built with London-New York route in mind. The plane was allowed into Washington, D.C., and the service was so popular that New Yorkers were soon complaining because they did not have it. It was not long before Concorde was flying into JFK. Concorde stopped flying over a decade ago. Since then, it has been revealed that over the life of Concorde, the plane did prove profitable. Concorde operating costs over nearly 28 years of operation were approximately £1 billion, with revenues of £1.75 billion. The last regular passenger flights landed at London Heathrow Airport on Friday, October 24, 2003, just past 4 p.m. Flight 002 from New York, the second flight from Edinburgh, Scotland, and the third which had taken off from Heathrow on a loop flight over the Bay of Biscay. In 2016, NASA announced it had signed a contract for the design of a modern low-noise SST prototype. There are many unanswered questions surrounding the potential return of supersonic flight, particularly in light of increasingly stringent noise and emission regulations. But you can't help thinking that if NASA can put a man on the moon, a rover on Mars, and take close-up images of Pluto, designing a more environmentally friendly supersonic airliner should not be beyond the realms of possibility.
This is the book review section for the present issue of ITSPodcast, reviewed by Dr. Haluk Eren, Fırat University, Elazığ, Turkey. The book title is Incremental Learning for Motion Prediction of Pedestrians and Vehicles, and consists of 158 pages, written by Dr. Alessandro Dizan Vazquez Goa. This book was produced by Springer in 2010. 9 chapters in the book are incorporated into 5 parts. The book is focused on motion prediction. Traditionally, dynamic and kinematic properties of pedestrians and vehicles are employed to predict their long-term motion. Here the author utilizes a next-generation approach, assuming objects are not in unpredictable motion. Using sensor data, their characteristic motion patterns could be learned and possible motion can be predicted. This book is divided in threefold: modeling, learning, and prediction. The modeling approach is based on hidden Markov models to represent the continuous state space of motion through a discrete approximation. The major emphasis of this study is modeling of the intentions in specified motion patterns, using state variables like position or velocity. In the learning stage, the main problem is taken as 2 parts, which are learning model via driving data and exploiting it to predict the motion pattern. To practice the solution into real environment, this book adapts HMMs to long-term learning. This application incrementally provides a topological map demonstrating the model structure and recalculates the model parameters. As a generic approach, the present solution could be designated for different ITS applications. The final stage in the proposed scheme is prediction, and real-time performance is achieved by Bayesian theory. The proposed approach was implemented and validated with experiments using both real and synthetic data. Real data was obtained by a visual tracking system mounted on a parking lot. For synthetic data, a developed simulator was employed for realizing proposed tests and examining the approach in large environments. This work is based on an award-winning PhD thesis. Existing chapters of the book are supported by relevant theory, a comprehensive overview and commands on the mathematical fundamentals of vector quantization and topology representing networks, computing fuzzy k-means cluster representations. Also, notation and abbreviations are given at the end of the book as individual appendices. Students, researchers, and professionals interested in next-generation learning methods will find this book a valuable reference.
Hello again. Are you ready for the prime content of this issue? Let's start with Professor Crane, chair of the IEEE Transportation Electrification Community, with a keynote he kindly delivered in our last ITS Society's Intelligent Transportation Systems Conference in the Canary Islands, Spain. He will be introduced by Professor Matthew Barth from University of California, Riverside, in his role of past president of the ITS Society. Enjoy!
Okay, so it's my pleasure to introduce the first keynote speaker. So Professor Philip Krein holds the Granger Chair in Electric Machinery and Electromechanics at the University of Illinois at Urbana-Champaign. He's worked in the area of power electronics and a lot of different applications related to electric transportation. And he's been in that area for about 30 years now, so he's been in that area, and it's been pretty in-depth career. So at present, he's the chair of the IEEE Transportation Electrification Community, and that's a community that the ITS Society has just recently joined. So with that, I'd like to invite up Professor Philip Krein.
Buenos días. Y bienvenido a Gran Canaria. That's about the extent of my Spanish, so we'll go to English, okay? Let's bring up this talk. Yeah, thank you. All right, so welcome everyone this morning, and I want to try and be a little bit provocative in thinking about what transportation electrification means in terms of some of the intelligent kinds of things that many of you are trying to work on. And I want to talk in particular about high performance capabilities, and also get beyond just vehicles and automobiles to some of the other systems kinds of aspects. So this morning I want to talk quickly about high performance drives and the kinds of capability that we expect to be able to see in these kinds of things. How quickly things can respond and what sorts of controls we ought to be able to do. And then I want to put that a little bit in context and think about fast energy restructuring, which has become very interesting in a lot of different transportation-related applications. And then maybe some examples, and we'll come back to the task here at the end, which I think is important. So, one thing that I think people underestimate, many of you I think may be familiar with this, but as soon as you build an electric traction system, you actually expect to get pretty high performance. So the kinds of mechanical bandwidths that you can create in an electric motor system are on the order of 100 hertz. Here's a fairly modest motor that we actually rebuilt into an electric drive system for a vehicle with plus or minus 100 Newton meter kind of response in roughly 10 milliseconds or so. This is considered standard. You know, you can buy those kinds of drives on the market. They actually put them into ridiculous applications like heating, ventilation, and air conditioning. Why you need 100 hertz bandwidth for a ventilation fan in a building like this is beyond my comprehension, but that's kind of irrelevant. The fact is, these are high-performance devices, but they're purely commodity, off-the-shelf kinds of things. If we want another order of magnitude, we can actually get it, but, we get that sometimes in robotics. I'm not sure we need it in transportation. Now, some of these have been used for a long time. I think some of you are probably familiar with active suspension systems. There was a lot of work on this in the mid-90s, and again, it's pretty easy to do the math and see that you can move equipment very, very quickly during an event and actually have an active suspension that has some real benefits and actions. This actually has become less interesting. There has been less work on it than there was in those early days, and I think one of the reasons for that, I saw a demonstration one time where one of these vehicles was tested, and they actually ran it over a curb at 100 kilometers an hour, and you couldn't notice. Okay, and I think at that point they realized that this vehicle probably wasn't going to be safe, because you could run it up on a sidewalk and kind of run it through a cafe, and the driver wouldn't necessarily notice, and that's probably not a good thing. So, the compromise between performance and safety remains a big issue, and I know many of you are working on that. This one I found to be a tremendous amount of fun. We actually, in the motor system I showed a little while ago, we decided to integrate that with a manual transmission, but, there's no reason to have a clutch. You don't need all these ridiculous mechanical devices that we use all the time. So, for example, this is a fully automated shifting system where basically as you move the shift lever, the motor responds and adjusts to the appropriate speeds. Everything is matched up, and essentially you can shift the car like this, and it will match up. You don't need a clutch pedal, and actually that car was incredibly fun to drive, because you can accelerate extremely rapidly, you can change through the gears, you can't stall the car, and it just works really well. So there are some interesting things that you can do at sort of this low level, but I want you to now think about how we can go up with that and do some more innovative things. This example, which Ford started in the late 90s, and Continental Automotive actually is packaging it up as a self-contained system. Basically, you take the flywheel for an internal combustion engine and use an electric motor instead, and you actually get enough bandwidth to offset the torque and vibration effects that you get because of a conventional piston engine. And you reduce the noise quite a lot, and you actually get much smoother operation and performance. And then you integrate that back into a start-stop kind of an environment, and then sort of what some people call a mild hybrid implementation. So really some very interesting things coming along in terms of conventional internal combustion engines because of this kind of electrification. Active control during events. I think some of you have worked on these kinds of rapid safety controls. But again, I want you to think about what I do with bandwidth at these kinds of rates. So, for example, when I started working on automotive, I found it very interesting that the highest performance, the best acceleration wouldn't necessarily be at zero wheel slip. You actually would have a little bit of a controlled skid going on to make things happen. And of course, now that a Tesla Model S can accelerate at about 1G, which really isn't supposed to be possible until when you think about the friction coefficients, we have to work on how do I actively control wheel slip, skid steering, and other things that one might do in an urgent safety situation. Of course, again, relatively routine, but I want you to think about taking that up an order of magnitude in terms of the time rates as far as what one can do with that. Now, what we've been doing more recently is trying to take advantage of high-performance controls of this type to do active system reconfigurations. Now, that didn't turn out so well, but basically that's the electrical system diagram from a Boeing 737. And the intention is to restructure it electrically over time periods of milliseconds so that, number one, you can manage safety situations very quickly. But number two, and perhaps more important in the long run, you can manage the energy flows to optimize efficiency in a very dynamic environment. And the impact is actually very high. And as a result, we've seen this picked up in a lot of other areas. So, for example, this is actually a diagram from an electric ship. Same general process. The rates don't need to be quite as high, and the safety issues are actually really a little bit more modest. But still, the idea of using electrical system reconfiguration for energy flows and for enhancement to get the maximum possible operating efficiency or to manage noise or any other kind of attribute of performance, we have the capability within the systems to do these things. And the intent of trying to use them and figure out how to integrate them dynamically into a system and take advantage of them, there's plenty of open questions. Now, I've been seeing some really interesting work at kind of the other end of the spectrum, very large off-road type vehicles. John Deere, for example, is working with us on dynamics of hybrid systems and electric systems related to mining equipment, construction equipment, and they are finding that it's not just about efficiency. So, for example, this device, a front loader, when it is built into a hybrid system, and that particular one, the 644, is a hybrid electric vehicle, they find that they can dramatically enhance 30-40% kinds of enhancements in productivity, because they can trade off the energy much more dynamically, and the operator finds it much easier to do things going back and forth. There's much less off time, there's much less downtime, and in fact, you can do more loads per hour. And, that doesn't sound like much, but in vehicles like this, it is absolutely all about that kind of productivity and how much material I can move during a particular operator shift. And when you're getting 30%, 40% gains, that comes immediately into a cost target. Collision avoidance, I know many of you have worked on that, but again, the question of thinking about what can I do with this? Do I need dynamic control, independent control of each of the wheels? That certainly is possible. And what do I do with that? What do I do with some of the things that I think some of you are working on, which is vehicle-to-vehicle automated collision management kinds of situations where we can maybe emulate some of the things we've already done with aircraft to kind of bring that about. I've been thinking about what could be done, for example, with dynamic crush zone reconfiguration. How do I actually use something like an active suspension kind of an actuator to reconfigure the vehicle during a really significant disaster situation, and maybe make it dynamically safer in that way. So there may be some things that you haven't thought of that we could try and do with this. Multi-unit traction. The Tesla Model S actually does use two motors, and they're integrated together. The battery pack there is actually in a flat pack that kind of sits under the vehicle. And those can be used together or potentially independently between the two wheels. So again, lots of physical capability. And in spite of the fancy appearance, those motors are actually significantly simpler and indeed cheaper than the electric motors that are used, for example, in the Toyota Prius and some other vehicles that may be familiar to you. Enhancement beyond traction, one of the areas that we continue to get lots of push for is in positive train control. So the electrification of the rail system in some sense is not complete, and actually we're going through another generation of that work, switching from DC to AC and going to higher performance systems. And the question is still open about how to make the best use of the dynamic capabilities of those systems for safety enhancements, operating enhancements, and ultimately automation. So how do these come back and kind of circle and close the loop on vehicle automation? I love this picture. Alan Mulholly, very proud of this wonderful EcoBoost engine, 3-cylinder engine, very, very good fuel economy. Look at that device. Okay? That is an internal combustion engine, one of the most complicated consumer products that we make. Lots of moving parts, very high precision, has to be made extremely cheaply. If I rip that apart and replace it with an electric motor, the level of simplification, the cost reduction, the performance enhancement, it's a complete no-brainer. I mean, it's not the least bit similar. So when we go to transportation electrification, it's win-win-win in lots of different directions in terms of enhanced reliability, enhanced simplicity, reduced cost, and then all the other things that come with that. We'll talk about some of the infrastructure challenges here momentarily. One of the things that I've been working on actually for many years is dynamic optimization. Again, trying to use the bandwidth capability and the dynamic performance capability much more actively, in this case for dynamic efficiency maximization. So basically in this case, a different level than the one we saw in the aircraft, I'm trying to take something like an electric car or a truck and dynamically reconfigure the energy flows, again, on millisecond timescales in order to maximize the efficiency at every moment in time. And you actually do see significant enhancements from this kind of thing. You're talking about 10 to 15% fuel economy enhancements just by having more dynamic optimization of what's going on. And the issue now is to take that to the next step. So if I can optimize efficiency, maybe I want to optimize other kinds of things as well. Maybe I want to optimize reliability. Maybe I want to manage device lifetime a little bit differently than I might in other ways. Many different trade-offs that can be put into that framework. One example relates back to hybrid cars. So there on the left is a typical engine brake-specific fuel consumption map. And there's that wonderful little sweet spot there. And I know this thing has a pointer on it. I see it. And I want to make sure I press the right button here. Yeah, there's the right button. So there's that wonderful little sweet spot, little area there. In a hybrid vehicle like that Nissan Hybrid Ultima, in principle, the electrical system can operate at dynamic rates such that it can push the engine right into that sweet spot almost all the time. That's not necessarily, in the end, that's not necessarily the right thing to do, because I want to optimize the whole system, not just one component. But nevertheless, you can see a strategy that starts to emerge from that as we put these things together. And then even during an acceleration and a deceleration, I can try and hold that engine over at least some narrow range of that high performance attribute, and can do quite a few different things with it. Nissan Leaf, here's a few examples. And I wanted to talk about this one in particular because when you run the numbers, you find out that the 120 kilometer range, 24 kilowatt battery pack, that, to me, that doesn't sound all that wonderfully impressive. You do the math on that, you're talking about, couple of hundred watt hours per kilometer. There's some old rules of thumb in the industry that I'll come back to here in a moment. The old saying is your mileage may vary. To give you an example of that, when we were working in some of the early days of electric vehicles, I had one undergraduate student who could get in the car, drive it, and get 30-40% better efficiency than anybody else who drove it. And nobody could really figure out why. You could watch him drive, you could ride with him, you couldn't really tell what was being done differently. So, for example, in that scheme of numbers, 200 watt hours per kilometer, he was able, with a car roughly similar to that one, to get something like 90 watt hours per kilometer. So it can be done. Okay? Now, the car has got to figure out how to do that. So that's one of the autonomous control challenges that we have coming up against us. I'll give you another example. I had a Toyota Prius for almost 15 years. My daughter could drive it and get about 20% better fuel economy than I could. I was a little more aggressive than her, but I have another daughter who would drive it and get 20% worse even than me. So, you get the idea, right? All of these are very sensitive to the details of how they're driven. And given that we can reconfigure them dynamically, it should be possible for the car to figure out how to drive itself in the best possible way for the situation involved. What goes around comes around, right? And we're kind of getting back where we were. Okay, so here's one of the leading high-performance cars from 1914, right? A friend of mine who was an IEEE Society president for many years actually bought this car and restored it. In 1914, electric vehicles dominated, and that car was considered a very high-end one. And by the way, the investors who ran the company that made that car had familiar names like Edison and Ford. So you get the idea, and we're finally coming back to the point where we can talk seriously about electric vehicles like this one, and not find it an embarrassing conversation. Tesla Model S, okay, the efficiency is not that impressive in some ways. Its standard ratings come out to something like 238 watt-hours per kilometer. I personally think a car is not terribly efficient if it's doing more than about 250 watt-hours per mile. So do the math. You'll figure out that, it can be a lot better than it is. Well, it's been optimized to impress the heck out of people who operate it. And anybody here who has driven one or who is lucky enough to own one, again, 1G acceleration, I hope people don't really use that, but nevertheless, it gets their attention, right? And there are a lot of other pieces of that as well. So, we're in that era right now where we're making a trade-off between what do I do with these performance capabilities? Do I knock people's shoes off and impress everybody? Do I maximize efficiency? Do I use them for safety? What are the objectives that I ultimately try to achieve with them? So we come back to a car like this one, the Chevrolet Volt, where again, range is kind of the objective in a car like this, but it tries to kind of reduce the battery pack size to see what can be done. It's got roughly 60 kilometers of pure electric range, and the emphasis then is on that vehicle as a plug-in hybrid. So we need to think about the context of that as we go along as well. This one, okay, I don't want it to be all about cars, right? So here's a Boeing 787. I took that picture, by the way, before they started having problems with batteries. Very interesting electric transportation system. More electric anyway. It's not, of course, fully electric, and it's not quite to the point where you'd call it hybrid, but nevertheless, the electrical design is quite dominant in terms of a lot of the new features. So, for example, it uses a variable frequency distribution bus, and has some other things related to that. Dramatic reduction in complexity of the mechanical linkages because of some of the trade-offs that have been made there. And again, trying to enhance reliability and safety as well as fuel economy. Ultimately, we'll get to this sort of thing. NASA is working on about 3 different concept vehicles for very high-performance electric aircraft, ultimately all electric, or certainly very formal hybrid electric, which is really the intent of this one, with a turbo engine that ultimately creates electricity, and then all the propulsion is electric and everything else related to that. And we will see these kinds of things. Right now, there's some very early tests. I think that one is, the target is to try and fly that in the 2025 kind of time frame. So there's several different projects going on with that. And I think ultimately they may end up with cryogenic superconducting electric motors to make that work, which sounds really bizarre until you start doing the math to try and figure out how I optimize the system. Okay, I noticed a few papers in which we talk about charging infrastructure, and I don't want to get off too much on that tangent, but I did want to at least put some of these things in context. So, as I work on electric transportation, lots of people say, well, what is this going to do to the grid? And I say, well, you're asking the question the wrong way. In the United States in the 1920s, the utility companies didn't say, oh, gee, what are people's appliances and what's growth going to do to the grid? Oh, this is terrible. No, it's, okay, now I can grow my business. I can do things that are new. I can sell product. I can make electricity. Electric transportation is very much the same way. But what about the infrastructure? So, for example, and this is an important point, right? Here's an electric vehicle charging station. At this point in the United States, there are about 250,000 of them, supposedly. I think that's completely irrelevant because there are about 100 million places where you can get one of those. Okay? Every one of those, if it's reasonably accessible, is potentially an electric vehicle charging location. Okay? We don't have to make this problem hard. We can make this problem easy. There are countries, quite a ways north of here, where there's essentially one of these, essentially at almost every parking space, because people need that in the wintertime to keep their cars warm enough to operate. So, this infrastructure is ubiquitous, and there's no reason to not try and work with it. So, challenge is how do you actually do that? So, how do you make this vehicle, right? This vehicle platform kind of an integrated part of the grid? And I think one of the tricks in the end is going to be, is there a business model associated with some sort of an aggregator who then puts these together so that the utility sees essentially one larger object rather than a whole bunch of individual things? I mean, one of the challenges, it's really a business challenge, is does a utility company want to interact dynamically with 100 million different vehicle drivers and negotiate rates and figure out charging and everything else? Well, it can be done, but it's a little bit of a daunting problem. Probably makes more sense to go through some kind of an intermediary to make that kind of thing happen, and then ultimately have vehicles that run on things like alternative energy resources rather than fossil fuels.
Hi again. Are you enjoying Professor Crane's talk? For sure you are. We are recruiting volunteers for the ITS podcast. If you like our show and you think you can share some of your time with us, please let us know. Send us an email to ITSPodcast@gmail.com. ITSSPODCAST@gmail.com. Also, it would be great if you could subscribe to our social media like Facebook, LinkedIn, YouTube, and more. You can find links to all of our social accounts at ITSP.CICEI.com. Thank you. Let's get now back to our today's main course.
Flexibility, okay? This is also quite important from the infrastructure perspective. Plug-in electric vehicles, I want you to think of them as, it's not a different kind of a thing. It's not a different animal, but it's what I call an energy load. So I want 24 kilowatt hours into the Nissan Leaf, and I want them there by 6 a.m. tomorrow morning. Okay? I really don't care how that happens. I just want to make sure that it happens. It turns out the way that the utility system operates in most of the world, certainly in the United States, is essentially based on energy loads at some high level. So one utility will call up another and say, hey, I need 200 megawatt hours between 2 and 3 p.m. this afternoon, and I'll pay you this much for them. Do you have them? Can you deliver? Yes, no, contract is organized, put that together, done deal. Okay? So the dynamic kinds of things that go on, this sort of thing is very much in the background. So we don't need to think of electric transportation as some kind of a different animal. It's an energy load that can be integrated in the system like any other energy load. What that brings about is flexibility. Okay? So if a typical passenger car is parked 95% of the time, then presumably I have 95% flexibility in terms of how I actually manage the charging process. And that's worth something. That's worth real money. So, storage costs a lot of money. Having batteries that go back and forth costs a lot of money. flexibility really doesn't cost anything. And we're used to it and something we can very much take advantage of. So, grid, like I say, grid infrastructure is ubiquitous. We need to make it more so. There's no particular barriers to kind of universal plug-in. There is one challenge, right? If I want to go very long distance and I really need quick charging, then sure, maybe I need some fast charging infrastructure at a few places. But in general, if I can drive to my destination and charge while I'm there, I don't have to make this hard. It doesn't have to be a hard problem. So how do we make the vehicles adapt to the grid? How do we make the grid adapt to vehicles? How do we take advantage and get the benefits of flexibility and really make this work? So there are plenty of good challenges coming up. Vehicle to grid, I want to talk about just very quickly. Really, your three elements would be a power connection to the grid, some kind of communication, and then suitable metering, and then trying to make this go back and forth and work out to everybody's mutual benefit. And of course, we talk about different charging levels, and I know that some of the terminology here is passé, but one of the interesting pieces here is that when you look at the fast charger I showed up before, which is kind of this middle range here, you think of these separate dedicated devices, okay? An electric car has roughly 100 kilowatts worth of power electronics capability already built into it. So having this off-board device that kind of duplicates that strikes me as a horrendous cost burden that really doesn't have to be there. So certainly the basic charging needs to be on the vehicle. It's got to be really convenient to just drive up to any point in the system and simply plug in. The same thing actually applies to here. If I can get an outlet basically that has more capability, I should be able to plug into that. And if I really need something rapid, potentially we'll have these commercial filling stations. I think actually roadway electrification may be more interesting in the long run, but there's still going to be some debate about this. But I think at this point the industry grossly underestimates this, and I think simply encouraging people to charge where they are and making that possible and easy and setting up the billing and all that, these are things that you folks can handle very easily. There's plenty of models we can build from. Now, we talk about, there actually is a lot of work on bi-directional charging. Here I have a vehicle of any size. It's got a battery system in it. I should be able to use it somehow as storage on the grid. Frankly, that's not that useful. And the cost is fairly high, because I have to have power electronics that's bidirectional. I need to worry about bidirectional safety systems. I have a lot of issues in terms of interfacing with the grid. But actually, it turns out that the flexibility, right? If I can take advantage of flexibility, I can get almost the same kinds of benefits. So if I can turn charging on and off, move it around in time, I can make this work. I don't really have to have bidirectional energy flow. And one of the things that does come out of this that becomes very important is you don't want this to be completely passive. You don't want any kind of transportation electrification to simply be an on-demand kind of a system, because that is counterproductive, right? Here was a study that somebody did on about 2,000 vehicles, simply uncontrolled charging, buy an electric vehicle, plug it in when you want to, heck with whatever else is going on. And sure enough, that tends to exacerbate the already well-established peaks early in the morning, late in the afternoon. And it requires, obviously we know how to do that, but it requires a lot of expensive infrastructure enhancement to improve it. But if I can take advantage of flexibility, then I can reduce the costs. I can encourage people to go and charge during times when rates are much, much lower. And as long as you can meet their objectives, you can do this either in a decentralized sort of a fashion or a centralized one. And ultimately, we can get controls like the ones that are kind of shown here. The very flat, very well-controlled lines here are based on having vehicles that are coordinated through the grid or through an aggregator, whereas the other things are having much less coordination. This is actually pretty severe. These are big frequency swings in the grid caused by random operation of vehicles, but by simply coordinating that a little bit, I can actually use them as a regulation resource. And again, it doesn't matter whether they're bidirectional or not, as long as I have some flexibility. So having the charging go one direction is not itself a barrier, right? I can use it in some intelligent way and treat it, in effect, as virtual storage. So in other words, if I need more energy, I simply stop delivering energy out to the vehicles that are already out there and take advantage of that. And of course, very fast dynamic capability that we've already talked about is something that I can take advantage of there. So with that kind of a system, even without having the energy flow going both ways, I still get millisecond response kinds of times with a charging infrastructure system related to electric transportation, and I can do a lot with that in the grid. The nice thing about this is if I do this in a virtual fashion, then growth is very much to my benefit. The more cars that are out there, the more trucks that are out there, the more vehicles that are out there, the more flexibility I have to take advantage of. So it's actually a huge growth benefit for these things. Now, I want to wrap up here a little bit. I want to talk just for a few moments about kind of keeping our eyes on task and some of the things behind here, right? So one of the things that we don't think about perhaps as much as we should is how do the markets actually adapt, right? It's easy to say here's what the public wants, but right, here's two people who are famous for ignoring that. Okay, Steve Jobs was very famous for saying, I don't care what people want, I'm going to make them stuff that they don't know they want, and they'll want it eventually, and I'll be fine. And of course, he did quite well with that. And curiously enough, Henry Ford was actually one of the people who instigated that philosophy, right? You remember his old line, right? If I gave people what they want a faster horse. Okay, so he got past that very early. And I think that is still true, that we need to make sure that electrification and transportation automation are chasing the fundamental needs, not necessarily what people are trying to claim that they want, right? Maybe they want a better Pullman, train car. Obviously, that company wasn't able to keep up with change, and doesn't exist anymore. There's a typical picture, right? So we need to keep in mind what we're trying to do. I think that the dynamic capabilities in electric transportation open a lot of opportunities beyond what many of you maybe are working on. Much faster dynamic capability, a lot of energy flexibility, many things that we can do that we simply can't do with more conventional platforms. And how do we take advantage of that, right? How do we take advantage of that? And also electric transportation as a partner in the electricity grid, which goes beyond just the vehicle-to-vehicle interaction, is a huge benefit. Now, does that picture look a little bit familiar? Okay. Somebody asked me whether that was Beijing, right? No, that's Manhattan in May 1973. I remember that. Okay. Took us a long time to get past that. I hate going to other places of the world and see people trying, having to relive this kind of history. Let's help them get past it. So, ultimately, right, eyes on task, mobility for everyone is certainly still one of the issues, right? And put you up some of those. I know some of you are thinking about this, but the question is, what do I really want to accomplish with an autonomous, active, and or electric kind of vehicle? And I want to go way beyond just enhancing the cars we have and think about mobility for everyone in the end, right? How do we get past stuff like this and still give people the transportation freedom that they want? Okay, so at that point, let me stop, and I want to make sure there's time for questions. Thank you.
Any questions for our speaker? Yes. We have a microphone.
think you'll have to shout it out. So.
Just speak.
Oh, here we go.
Thank you for the impressive talk. And as you may know, Toyota has started selling the revolutionary hydrogen vehicle called Mirai. Can you give us some comments about this vehicle and the perspective of this new hydrogen energy versus the electric car?
So I didn't catch all of your question. You're talking about magnetic rail systems?
No, the new hydrogen vehicle.
Hydrogen.
Yes.
Okay.
Called Mirai.
Yeah. Hydrogen. Okay. So that could be about 3 more talks. So the issue of powering vehicles with hydrogen, okay, put it in a different perspective, right? Vehicles powered with protons versus vehicles powered with electrons. Okay. I actually put a homework problem into my textbook, asking students to think about, transporting energy in the form of hydrogen versus transporting energy in the form of electrons. One of the actually very interesting things, fuel cells, right? They're wonderful. Lots of people are developing them. In mobile applications, fuel cells are fundamentally limited in their efficiency, probably to about 50%. Maybe a little bit more. A really, really well-designed turbo diesel hybrid electric vehicle is about 50% efficient. So, there's a lot that we can do with more conventional technologies. Now, lots of people are working on that. We'll see, right? The fuel cell in my career has always been the technology of the future. Maybe it always will be. Space program will have plenty of opportunities for that. And there are some really good stationary applications, actually, for fuel cells. The mobile ones I'm much more skeptical about now. Other questions?
Thank you for the presentation. Now, the question I have, so you're going to optimize it based on a driver. Regardless of the driver, the car is going to optimize its behavior or self. Mm-hmm. So what about can we then incorporate the road, the topology of the road to optimize the vehicle? How do we, maybe the situational awareness of the traffic mobility, how would you see that?
Well, and that's, okay, so that's a really interesting question. When you start to talk about optimization, right, there are many different ways that you can attack that problem. One, of course, is kind of the device and component level. So as I showed, you try and optimize and maintain an engine operation in a sweet spot on a fuel consumption map. The other is dynamically, locally within the system. So right now I try and optimize moment by moment energy consumption. But of course, in reality, what am I really wanting to optimize? It might be time, right? It might be fuel consumption over a particular path. Trying to go from point to point. And of course, obviously the driver has some input as well, and it's going to depend on the topography of the road as well as the quality of it and everything else. So I think as we can take better advantage of the dynamic capability, we can start to open that problem up a little bit more and actually think of it that way. And certainly, and again, I think that's where the electric transportation really begins to interface into the intelligent system, is how do I now take advantage of this and do, a larger and larger optimization, still focused perhaps on the individual, but, ultimately, over a course or over a target path. I mean, for example, we're trying to do optimization over particular kinds of drive cycles and that sort of thing as well.
One more question? Do you want to make a few comments on battery technology?
Battery technology, oh man. Well, batteries are the limit, right? They always are, always will be. They're really not. I think Tesla has already pretty much shown us that there are ways to deal with this. And again, when I think of, there's a huge dichotomy, okay? On the one hand, An automobile is parked a lot of the time, and therefore the batteries ought to be charged essentially when they're needed. But for example, long-distance trucks, right? They're only useful to the extent that they're in operation. So it's a different world. I had the chance, for various reasons, I actually drove across the United States twice during the spring basically from Sacramento to Chicago. There is about 2,000 miles of corridor of Interstate 80 where there's essentially nothing there. To electrify that corridor, not just put it in the roadbed, I mean, we could put overhead. We could do a very conventional catenary system for the trucks. It wouldn't be hard. Okay? And you can see it, right? You can drive down that highway and see how that could be put together. So there actually are quite a few alternatives that we need to think about in terms of the differences between long-haul requirements, short-range requirements. Getting enough range to go around in a city, I think is a solved problem, frankly. Getting enough range to go long distance, it's either a hybrid kind of a solution, as we've seen, or it's some other kind of electrification solution. Which one is best, I think, remains to be seen, but I think we need to think, again, more globally about how we optimize the entire system. Thanks.
Thank you very much. Let's thank our speaker.
Well, this one is over. We hope you have learned a thing or two about one of the most exciting movements in the intelligent transportation arena, which is transportation electrification. Apparently, we will be seeing more and more of this in the near future. Please send us your comments. We work all year round for the benefit of our precious listeners. This podcast is sponsored by the IEEE Intelligent Transportation Systems Society, website designed and managed by the Innovation Center for the Information Society at the University of Las Palmas de Gran Canaria in Spain. Soundtrack developed by Rubicon, audio edition and post-production by the Institute of Cybernetics at the University of Las Palmas de Gran Canaria. I'm Javier Sánchez Medina from the IEEE ITS Society. Thanks very much for listening to our show. We'll be back soon bringing you again the cutting edge of science at the Intelligent Transportation Systems podcast. Have a happy end of the summer and drive safe.